Welcome to this explainer. Look, as senior systems architects, we're going to bypass the casual hype, the sci-fi tropes, and the superficial summaries right out of the gate. Today, we are diving directly into the structural reality of deep learning. We're going to unpack the exact mathematical mechanics that allow these systems to function, optimize, and actually be deployed in the real world.
First, we have to completely strip away the anthropomorphic metaphors. A machine doesn't actually learn in the human sense. Instead, we have to ask how mathematical optimization simulates learning. What we commonly call artificial intelligence is fundamentally just a highly advanced series of matrix transformations driven by calculus.
Here's our sequential syllabus for today's breakdown. 1. The deep learning paradigm. 2. Architecture of neural networks. 3. Computing the loss function. 4. Optimization and gradient descent. And 5. Real-world deployment reality.
Section 1. The deep learning paradigm. Before we start building a network, we absolutely have to define its foundational logic and operational mandate.
Let's anchor ourselves on this core definition. Supervised learning is strictly about mapping an input matrix to an output prediction. You start with an input, x, which has to be encoded into a numerical vector. This could be anything, the age and mileage of a car, or a 10-second audio clip sampled at 44.1 kilohertz, which gives you an input vector of 441,000 integers. The entire objective here is to construct a mathematical function that processes this fixed-size input x and reliably computes the correct target output y. In semantic segmentation, raw RGB pixels are computationally mapped into structured, segmented arrays. Your input X is a massive dimensional grid of color values representing, say, a street scene. The model's task isn't just to output a single simple label, it has to produce a highly complex, structured output Y, a secondary mapping where every single pixel is classified as background, a vehicle, a pedestrian, or a bicycle. The mathematical complexity of that mapping from X to Y is staggering, and that demands a very specific type of internal topology. Section 2. Architecture of neural networks. With our mapping paradigm locked in, we transition to the internal topology required to actually process these massive dimensional inputs. A simple linear equation just can't map a million pixels to a structured semantic output. We need depth. Information flows sequentially, starting from the raw data vector in the input layer, moving through the hidden layers, and ending at the final output prediction. The input layer ingests the numerical representation of your data. Then the hidden layers apply nonlinear transformations, essentially warping and folding the data space to extract meaningful features. Finally, the output layer synthesizes those transformed features into the final prediction, y. That's the physical architecture. But remember, an architecture alone doesn't do anything without a method for improvement.
Section 3. Computing the loss function. To force this network to learn, we have to introduce a rigorous mathematical mechanism to measure its failures.
A network that can't quantify how wrong it is can never become right. By calculating cross-entropy, we quantify the network's error. This creates a precise target that our system has to minimize. We rely on principles like maximum likelihood to construct these loss functions. Whether you're using binary cross-entropy for a simple classification or far more complex formulations, the goal is always singular. Generate one numerical value that represents the exact mathematical distance between the network's current prediction and the actual ground truth. As an engineer building these systems, this loss is your absolute baseline metric of failure. Section 4. Optimization and gradient descent. This brings us to the dynamic climax of our architecture. We have the structure, we have the measure of failure, now it's time to optimize.
When a network initializes randomly, it basically drops onto a high error coordinate on a conceptual loss landscape. The parameters of the network, its weights and biases, start out as random numbers. Because of that, its initial predictions are essentially garbage, which means a very high loss. Imagine a topography where lighter colors represent high error and darker colors represent lower error. At initialization, the network is flying blind, sitting right at the top of a mathematical mountain of error.
The crucial breakthrough here is backpropagation. Backprop uses the chain rule of calculus to calculate exact derivatives, figuring out precisely how a tiny change in any single parameter throughout the entire network will affect that final loss number. Once we have these derivatives, the gradients, we know exactly which multidimensional direction points downhill toward less error. We then update the network's parameters, the slopes and intercepts, to take a step in that steepest downhill direction, and we just step iteratively. This is gradient descent in action. The system steps down the mathematical topography until it settles at the optimal global minimum. You can conceptualize it as progressing steadily down into the darker, low-error regions of that landscape. The algorithm is continuously recalculating the downhill direction and adjusting parameters. Once the loss hits its lowest possible point, the network has successfully mapped X to Y with the highest possible mathematical accuracy. At that point, your model is considered completely trained.
Section 5. Real-world deployments reality. We now have to connect this abstract optimization theory directly to the engineering challenges of deployment.
Because as any engineer knows, what happens in a pristine training environment rarely survives first contact with real-world data. When diagnosing a model's failure in production, we orthogonally separate avoidable bias from variance. This ensures we deploy the correct structural intervention. If your training error is significantly worse than human-level performance, you have high avoidable bias. The engineering solution? Increase your model capacity or just train longer. But if your training error is fine and your development set error is terrible, you're dealing with high variance. The model has basically memorized the training data and can't generalize. The fix for that is entirely different. You need to apply regularization techniques or acquire much more diverse data.
In modern deployment, we rarely train models from scratch. We take massive, pre-trained models and adapt them, and depending on your constraints, you have to choose between the speed of feature extraction or the deep representational shift of fine-tuning. If your new task is very similar to the original training data, you can just freeze the existing pre-trained layers, append a new output head, and train only that head. It's computationally cheap and very fast. But if your target dataset represents a major structural shift, you have to use fine-tuning. That means carefully continuing to train all layers with a very small learning rate. It's slower, but it's absolutely critical for complex dataset shifts.
Now, beyond the math, we inevitably run into the alignment problem. This is where we have to separate technical solutions, like preventing a reinforcement learning agent from reward hacking its environment, from normative challenges, like actually defining human values. Technical solutions exist for technical problems, but deciding which values, whose cultural norms, and what societal rules to mathematically bake into these optimization functions, you can't solve that by just adjusting a learning rate or changing a loss equation.
We're going to conclude this explainer with a masterclass level question. As we train these architectural blueprints on vast amounts of intellectual property, whose moral conventions are we actually optimizing for? We are taking the world's copyrighted material, scraping human history into fixed-sized input vectors, and optimizing it all down to a global minimum. The math of backpropagation and gradient descent is entirely objective, sure, but the data landscapes we point them at are entirely human. As system architects, you aren't just minimizing loss, you're standardizing a worldview. It's something to think very carefully about when you choose the coordinates you initialize on.